Today I will talk about or research with various people on the quantum critical behavior of biomolecules. So I would like to say a few words at the beginning how I got into this topic. As you heard, I spent my postdoc years working on quantum chaos, which is how systems which are classically chaotic, how they behave quantum mechanically, which was a very important topic in the 90s and in the 80s. After that, my interest turned to various complex systems, and I did lots of interesting work on totally different systems. So I was, in general, by the time I got to this topic, I was a little bit outside, for 10 years outside of quantum mechanics, partially because I thought that nothing important will happen there. And then I was a fellow of Collegium Budapest in Hungary, and my biologist colleague brought a visitor, and we had lunch together. They arrived late and I arrived late for lunch, so we were sitting at the table, and there was an old guy, not this young. This is from 30 years ago. And I met Stuart Kauffman, who you might know, who was one of the fathers of complex systems in the 80s and 90s, and was one of the fellows of Santa Fe Institute. And as we were discussing various things at lunch on complex systems, he was basically not interested in any of the topics I brought up, and he asked me, Gábor, what are you by profession? What is your original field? And I said, physics, quantum chaos. And he said, quantum, and I need a quantum physicist right now. And we started talking for 3 days after that. And he convinced me that there are new developments in biology which indicate that there are quantum effects actually in biology beyond what we know about quantum chemistry, etc. And that this is a very exciting topic. And I also probably you know that Stu was the pioneer of looking at gene regulatory networks and developed Boolean networks. And he and his colleague Chris Langton in the 90s coined this statement that life is at the edge of chaos, meaning that living systems are neither ordered nor totally chaotic, but are somewhere between. And the reason was that sort of ordered systems are boring and go to some very trivial behavior. Chaotic or stochastic systems are very irregular and cannot sustain life. And somewhere in between, there is a proper dynamics for life. And they actually formulated this, that living and computing systems work at best at this point, at the edge of chaos, sometimes on the upper edge, sometimes at the lower edge, from order to the chaos or back. And and so they realized that these systems, which are neither totally chaotic nor totally regular, but are somewhere between, are the most important from the point of view of both biology and computing. And later on, it turned out that actually many of the, or almost all the complex systems which we know are somewhere in this in this regime between chaos and order. Okay, and by the 2010, this was so obvious that I just cite a random paper from Bialek that this is a paper collecting examples from various parts of biology, proving that systems from bacteria to the swarms of birds behave as if their dynamics would be on the border of chaos and regularity. And we call this regime the critical regime because this is where a phase transition happens from ordered to critical, from ordered to chaotic, or from chaotic back to order, and somehow all these systems tune themselves to stay at the border in their parameter space. They don't sit in the chaotic regime or in the ordered regime. They always sit in their critical points of their parameter space. And then the question came whether if biology shows quantum effects and if quantum effects play an important role in biology and in evolution, how is it related to the same thing in quantum mechanics? Because in my studies from my postdoc years was on quantum chaos, chaotic systems, and we knew very well that by changing the parameters of chaotic systems, they might become ordered, and between order and chaos, there sits a regime where they can be critical. And in quantum chaos, this critical phenomena is sort of has been studied since the mid-90s, and the origin of this topic came from Niels Bohr or from nuclear physics, when they studied the nucleus in the 30s, 40s, and on. They could see lots of sort of energy levels, resonances of the nucleus, and they produced a model which could describe all these resonances. And these pictures are from Niels Bohr's original paper in Nature from 1936. So in the nucleus there are resonances, and this illustration shows that if you see lots of energy levels, a very dense set of energy levels, and you increase, you look at them in more details, then you can see really the individual levels, and then you can study the spacing of the energy levels. So the spacing of the energy levels, we know that in quantum mechanics, energy is quantized, and these quantized energy levels can take various forms. Here there are a few examples. For example, if we have a system like a harmonic oscillator, we have energy levels regularly spaced, and we get a totally uniform distribution of energy levels. And then if we look at these nuclear systems, you can see that there are energy levels which are close and far, and there are various spacings. And then later on, people realized that depending on the dynamics of the system, there are two main classes. If you have a chaotic system, like this is named after the famous Russian mathematician Sinai, who invented the Sinai billiard, and people quantized that, and they looked at the different energy spacing. So spacing is the difference between the energy levels, these sizes of these gaps. And if they look at the statistical properties of this chaotic mathematical system, then it will be very similar to this nuclear system. Actually, they share lots of statistical properties. And then these properties are shared also by the spacings of the prime numbers or Euler zeta function zeros, etc., etc. So they observe that there is some universality in nature, so that certain systems which are totally different by origin show the same energy level distance distribution. And basically all these systems show the behavior of the chaotic, so a quantum chaotic system has a certain level spacing distribution, and all these systems show that. While there are systems which are quantum regular, so-called integrable systems, and their energy level distribution is different. Energy levels like to sit close to each other, and if we look at them all over, then they form a Poisson distribution. It's like a set of randomly placed energy levels. If energy levels look like totally random, they have a Poissonian statistics, and ordered quantum systems all show these statistics. So going into more details, what we
Gábor,
can see, yes?
Just a quick, what were those little carrots on the side on the Poissons and the primes that are highlighting specific energy levels? You see those little triangles? Or
these
yeah.
are nothing particularly interesting for us. I just borrowed this from another presentation, and okay, but for today we don't need them. So these are just regular. This is just 50 energy levels from various physical systems. And then Wigner and Dyson in the 50s, they developed a very nice mathematical theory of this, and they showed that if we sort of take a random quantum system, so we just take a random matrix, you know that Hamiltonian is the eigenvalues of a Hamiltonian matrix are the energies in quantum mechanics, and if we just would pick a totally random Hamiltonian with totally random numbers in the matrix entries, then we calculate the energy levels, what we will get is, which is since then called the Wigner distribution of the energy spacing. So if we look at the spacing between the energy levels, we get this single-humped curve, this red curve. On the other hand, if we just have random energy levels, they are Poisson distributed, and the distance between the energy levels will be an exponential. So we get this black curve for the distribution of the energy differences. These two curves are sort of universal, because as long as a system is sufficiently chaotic, then no matter what are the details and no matter what kind of particularities the system has, this level spacing distribution will be universal. So it will not depend on anything else, just the symmetries of the system, like if the system has a time reversal symmetry or doesn't have a time reversal symmetry, then these curves will give you slightly different universal distributions, but there are only a few universality classes, and all systems should fit into that. Also, if you look at the normalized density of states of these random matrices, they will form this famous semicircle distribution. So the energy levels of a random Gaussian matrix will form a semicircle. Okay, and then what happened that in the 80s and in the 90s, people were very excited because they could check if what happens with classically chaotic systems. So if we took the cyanide billiard and looked at how quantum electrons would behave in this cyanide billiard, and we would get the energy levels of the system, the distances of the energy levels form the same distribution discovered by Wigner, which is also called the GOE, the Gaussian orthogonal ensemble distribution. Why, if the cyanide billiard is just a square and there is a circle inside, and the electron can bounce between in this box and can bounce back from the circle. And if we remove this circle, then we get a regular system, and this disk rather, then we get the Poissonian level distribution. Okay, and in the end, by the middle of 90s, it turned out that that beyond these two categories, which are related to chaos and order. So for a chaotic system, we get the Wigner distribution of spacings. For a regular system, we get the Poissonian distribution of levels. In between, if we change some parameter in the system, and we can change that system from ordered to chaotic, there is a point in the middle where the system is neither ordered nor chaotic, and then we get a very special spacing distribution which exists only at this border. And this distribution is here, and it is similar to a little bit to both the Wigner distribution, because it starts linearly, but the tail is exponential, like in the Poissonian distribution. So it's a it's somehow the combination of the two, and this distribution exists only in the critical point. If you change the system and move it from the critical point, the distribution changes to Wigner or to Poisson. And later they realized that this is not just in chaotic systems, but the same behavior is observed in disordered conductors. So if you have a lattice and electrons can hop on this lattice, and this is a minimal model of a metal, and you put some disorder on this lattice, so it will be like a disordered metal, then first the system behaves like a chaotic system. All the states are somewhat mixed, and if you look at the energy level statistics of such a system, you will get the Wigner distribution. And if you put lots of disorder, your system becomes localized, and if you look at the energy levels of that system, this will be Poissonian distributed. And in the middle, so if you have high disorder, you get localized states and Poissonian level statistics, and your system is not a good conductor because the electrons like to be localized in these localized states. At the other end, you get metals just slightly disordered, and there is an almost perfect conductance from one end to the other of the system. And at a critical point, at a certain critical level of disorder, you get critical states which are neither localized nor extended states, but sit in somewhere in between, and this system is still a conductor, and somehow these states are in between localized and delocalized. You can see these peaks, so they look like some localization, but they are distributed, so they also look like extended. And if you take a closer look, these are fractal or multifractal states. So if you look at, you cut the wave function at some level, you look at this cross-section, and this cross-section will look like a fractal. You can calculate its fractal dimension, etc. So it's similar to other fractals which we learned long time ago about. Okay, and then how is this related to quantum biology? So, and this is what we got after 3 days spending together with Stuart Kauffman, is that if we strongly believe that life exists at the border of chaos and regularity, then quantum biological systems should exist somewhere close to this critical line between quantum ordered and quantum chaotic. Okay. So this was just a generic idea, and so let's have a look whether this can have any place in reality or not. And then the state of the discussion about quantum effects in biology was, and is, that open quantum systems like biological systems, if they are quantum, can lose coherence very, very quickly. Why? Because in physics, temperature should be low and the system should be separated from the environment, and in that case we can see some some quantum effects. And still, if you think about quantum computers, all this engineering and physics goes into this problem. They have to cool the system, and they have to separate it from the rest of the environment to get a precise quantum system. And biology is completely the opposite. There is high temperature, and there is a strong coupling to the environment, and all the elements are strongly coupled in biology. Molecules and other constituents of biological systems are always very much coupled. So physicists' view is that there cannot be coherence in biological systems. So then we know that in 2007 there was this famous paper from Engel and Fleming, and I think Greg will present here very soon. They discovered that in light harvesting, the transport of an electron or of an excitation from the photon. So a photon hits the chlorosome, and then the excitation goes through the so-called FMO complex, and they studied this complex, and they observed that actually there are quantum beats in that system, and not just at nitrogen temperature, but also at room temperature. They could all observe these quantum beats, and the question was that how can it be that we observe this in such a strongly such a biological system which is strongly coupled to its environment. And then our thinking was that so how is chaos, order, and criticality in quantum chaos related to the problem of coherence? So if we have an extended state, so long quantum state from one end to the other of the system, and we add some noise, then this state can fragment, rupture very quickly, and we lose its coherence very quickly. So if we have an extended system, it is vulnerable to environmental noise, and coherence will be lost quickly. And so if we would like to have long distance charge transport, for example, which is the most important thing in biochemistry in general, then these extended quantum states are not good for that in such an environment. Localized states are very good because they are coherent for a long time, because they are tiny, and if you add some noise, then they move together, and it's very difficult to move different parts of a tiny system in different ways, so they will preserve coherence for a very, very long time. But these systems are not good for transport because they are very much localized, so the electron will stay in one point of the system and will not move to any direction. So this is very trivial. Localized systems are insulators, and there is no transport. But then systems which are at the border of chaos and order, or localization and delocalization, are sort of have both of these good properties. Because they are somewhat localized, it can be that, that they can keep coherence for a long time, and they are also good conductors because they stretch from one end of the system to the other end of the system. Although they are fractal, yet they can carry charges from one end of the system to the other end. And so these systems can stay coherent and can transport charges. And our first work was concerning this system. So we looked at a disordered conductor, and we looked at the drop of quantum coherence in that system. And we realized that until the system has low noise, the coherence collapses very quickly. These are purity is a measure of the coherence of the system, and W was the strength of the noise. And when we added little noise to this system, then coherence was lost very quickly. And when we add strong noise, then coherence stays in the system for a long time, but it is not very useful. And at the border of these two regimes here, we get an interesting phenomena where the coherence decays only like a power law, not like an exponential here. And it can still carry charges from one end to the other end of the system. So these are good conductors, and the coherence decays only like a power law. So after that, we saw that the idea in principle is okay. So what we said, okay, quantum chaotic systems critical quantum chaotic systems stay coherent for a long time, and then it must be an evolutionary advantage for a molecule to be in this critical quantum chaotic state. But critical molecules don't arise randomly. I just told you that it's very difficult to tune a system into the critical point. It has a huge parameter space, and the very tiny part of this parameter space is actually where the molecule is critical. So you have to play a lot in laboratory if you would like to get a critical quantum chaotic system. Actually, just to get a solid state physics system to behave quantum critically was a horrible experimental challenge in the 90s and 2000s. So naturally, if molecules are anywhere, you will not find the critical molecules just by accident. And if we are right, then naturally evolved molecules which have some biological functions, and this criticality is beneficial for the function, then we should find lots of molecules. And we turned to Denis Salahab's group to Calgary, and they calculated several interesting molecules. So we were just guessing what kind of molecules we should check, and we just took random molecules from Wikipedia, and then so Theophylline is some kind of natural substance, and we looked at the energy spacing distribution, and this guy has only 100 levels, 100 energy levels. I'm talking about the electronic levels which are involved in the transport. And the surprise was that even with this low number of levels, if we looked at the level spacing statistics, it was neither GOE or Wigner distributed nor Poissonian distributed, but was sitting on the critical line without any tuning. So we just took the data, made the plot, and it was sitting there on the critical line. And then we took another, and then we took another, and then we took another, vitamins, etc. And they were all sitting on the critical line, but the statistics wasn't very great because we just have this order of 100 levels. So we can see deviations here and there, but the beginning was very, very promising. And then...
how do you choose the parameters of your Wigner distribution and your Poisson?
Oh, there are no parameters.
Oh.
These are all parameterless, both the molecules and the theory, parameterless. So you just take the energy levels, look at the energy level distances. You normalize the energy level distances with the density of states around that energy level. This is an extra step. And then you get a well-defined distribution without any parameters. And then you plot it against this simple distribution. And they are either the same or different. That's it.
So you normalize relative to the density of states for your object? Is that
yes,
right?
Okay. Yeah, in a real physical system, and a level spacing can vary a lot throughout the system. So the already in the nuclear physics in the 30s, they realized that they have to first calculate the density of levels. It's a smooth function as the energy changes, and then you have to measure the distance of the energy levels relative to the average distance of energy levels in the same area, same energy range.
Please define the X and Y axes. You've lost me a little bit.
Okay.
As to what you're actually measuring.
Yes, horizontal axis is the level spacing. So one means that the energy difference between two levels is the same as the average distance of two energy levels in that energy interval. And this runs from 0 to 5. And the vertical axis is the probability. It's a cumulative probability running from 1 to 0. So this plot shows you what is the probability that a level distance is bigger than something. And you can plot this for the theoretical curves. So this is the Poissonian theoretical curve. This is the Wigner distribution. So this corresponds to quantum chaotic systems. This corresponds to quantum ordered systems. And this one in the middle corresponds to the critical distribution I just showed you. So we plotted the energy level distances against these three theoretical possibilities without any parameters. So neither the molecules nor this had any parameters in them.
Sorry, I didn't quite understand. So why is there no free parameter in the Poisson distribution?
Because it is, the Poisson here means exponential. Because,
yes, but there can be different exponentials.
Yes, but if you normalize the energy distances for the average, then you should get a Poisson distribution with 1 as an average distance. So it is simply the e to the minus x distribution without parameters. So after you normalize for the average, your Poisson parameters should be 1.
No, go ahead.
Yeah, so if I telling you an example, if you have 10 centimeter and you line and you put 100 points on it randomly, and then you measure the distances of the points, they will be exponentially distributed, and 10 centimeter divided by 100 or 101 will be the average distance between the but you measure the distances of the points relative to this average distance. So in average, your normalized distance will be 1. And then if you plot that normalized distance, that will be simply the e to the minus x Poisson or exponential distribution.
Okay, may I ask another question? Because I mean, so you choose a few molecules here, and they were obviously kind of organic molecules. If you take inorganic molecules, what will happen then?
Yeah, it's maybe we can return to this
sure.
in the end. Yeah. Okay. So then there were counterexamples. So this is an organic molecule, and it has a Poissonian energy level distribution. Or here is another one, which is testosterone, and steroic molecules are generally follow the Wigner GOE distribution. But it's interesting that they roughly follow one of the curves and not something in between. But after that, we decided to look at bigger molecules, because then we get a better statistics and we learn more. And we looked at proteins, and we looked at proteins which are sufficiently large to get lots of energy levels, but sufficiently small to be numerically accessible. And we took 3 different proteins. One was these were, one of them was myoglobin, the other was insulin, and I forgot what was the third, but all these were highly important biological molecules. And these have something like 6,000 or 7,000 energy levels. And as we looked at their energy levels, they were absolutely precisely on the critical line. So if you look at the distance between the distribution what we got from the molecule and what is the theoretical distribution, there was less than 2% difference, which is the same as we, for example, have in quantum chaos. So the Sinai billiards energy level follow, I don't know, the theoretical curve with less than 2%, roughly the same precision. So up to model precision, they were the same. And we looked at then more systematically molecules. Because time goes by, I don't go into the details of the analysis, but what we found that proteins which were involved in biochemical processes were all critical. Then if you take silk, for example, silk protein was Poissonian. And then we took lots of different biological molecules. They were all critical, except those biological molecules which have no role in biochemistry. For example, if you take silk, which was one example, is just strengthening a structure. Or if you take molecules from fibers, then they are also not carrying electrons. They are just structural molecules. So all the structural molecules which just strengthen the body or whatever, they were Poissonian because it's better for them not to be insulators and not to take part. And we could find only steroid molecules in the chaotic regime. And then we could also check the wave functions of these proteins, and they seem up to normal analysis. They look like multifractals, and we could measure the multifractal dimensions. So if you look at the energy levels of a protein and the wave functions, and you enlarge a little part, you can see that it is very much similar to the whole of the wave function. So not just the energy level distribution, but also the multifractal wave functions were there.
I'm sorry, maybe I didn't follow this. What do you mean by wave function here? I mean, this is in a way a huge many-body system. So you cannot. Can you really represent the entire wave function?
Yeah, in normally you take a crystal structure of a protein, and then you calculate the electronic levels, and you separately calculate the vibrations of that. And like in solid state physics, you start from a picture where you have phonons and electrons. Mm-hmm. Then, of course, you have higher levels of interactions of structures, but in quantum chemistry, they just calculate the energy levels of. Yeah.
Sorry, no, carry on. But no, so I didn't quite understand that, because which method was used to actually compute this wave function? Because really the entire wave function of the system cannot be written down analytically. It's far too large.
Yeah, yes, this is a numerical procedure. So in quantum chemistry, there are various methods to calculate the wave functions of the electrons. And then there are details like core electrons, and then there are valence electrons, and we are talking here about valence electrons, etc. And then there are standard procedures to calculate.
That's right, but they have considerable error in them. So especially for the relative distances. So how reliable, so what I'm wondering is how reliable really these statistics are, because there will be, from my experience, there are sizable errors in that. And that can very well affect the statistics in the level spacing, in particular in the level spacing.
Yes. I'm talking about the state of the art in quantum chemistry. That's why we collaborated with this group in Calgary. We can discuss this also later. I can tell you more about the method we used here.
Right.
Okay,
perhaps you can, we can discuss.
I just would like to close this, that after finishing this paper and putting on archive, while I was visiting by accident Arizona State University, I got an email from Arizona State University, which I left in my mailbox to read after my return home, which was a huge mistake. And these two guys, Paul Davis and Stuart Lindsay from Arizona State University, sent us an email that they actually have a very interesting measurement at Arizona State University. And they discovered, I mean, Stuart Lindsay's experimental group discovered that actually when they measure precisely single protein molecules, large proteins, in this case it was integrin, which is a huge protein, it doesn't fit into the quantum chemistry calculations. And they observed first that it has a very large conductance and way higher than one would expect. They measured it between electrodes in a specially designed system. This shows you the molecule between electrodes, and then they could measure the conductance at various geometrical situations, and they could make accounting statistics about the conductance, and they discovered peaks in that. But the important thing was that the conductance was really huge. And we started working on Landauer formula, which could describe these systems and which would include or the idea that the protein is highly conductive based on the previous theory. And they also measured proteins between electrodes and their statistics, which we could finally reproduce using these formulas. And then there were other measurements. So there is another experimental group in the Weizmann Institute led by David Cahen, and we are working with them on the temperature dependence of myoglobin, azurin, and other proteins. And the important thing is that further developing this idea I was talking about, you can have predictions for the temperature dependence of the conductivity of these proteins, and we could reproduce these experiments in the last few years. So it seems, and here is where I would like to finish, is that it seems that this sitting at the border of order and chaos is not just beautiful, but it really has a biological function, and it speeds up electron transport at normal environments. So this makes the molecule really strongly conducting, and you can preserve a nearly quantum level conductance in such a biological system. So we are very close to the point when we can say that large proteins conduct with a conductance which is just a fraction of the basic quantum unit of conductance. And the reason is that they have this evolution really selected molecules for biochemical processes which have these very good wires, which are sort of the results of quantum biology, and we hope to publish very soon something in this direction. And I want to
do you see
thank you. Pardon?
Oh no, I'm sorry, I didn't mean to cut you off. Go finish what you were saying.
I just have to one slide.
Yes.
And after this, I actually learned that we Hungarians highly value Albert Szent-Györgyi, because he was the only Nobel Prize winner who actually was working in Hungary while he got the Nobel Prize. But no Hungarians ever learned what he did for the long period after his Nobel Prize and his death. And if you look at his works, he was actually very much into this subject. He realized that proteins should conduct very well, and the transport should be very quick. And as examples, he was working on the photosynthetic system, and he was looking for the common energy levels of proteins. And a huge army of quantum chemists in the 60s and 70s was working on these ideas, and they failed at that time because they didn't have the right experimental equipments or miniaturization, so that they couldn't measure single proteins. But it seems that by and large, his ideas about the strange quantum mechanical behavior of proteins seems to be very well funded. So I'm really happy that I could contribute to this work as well. So I would like to thank you. And I'm open